So recording is in progress. Share the screen, press share, shrinkify that, move that down the right-hand corner. Okay, now we are ready for today. And today is more testing O hypotheses. So continue on with our world of hypothesis testing. Let's go take a little trip down history's lane. There was this guy in Austria. He was a monk. They didn't make a TV show about him, but let's see, when did we do this? Back in the 1800s, the internet wasn't invented yet. They didn't have cell phones. The printing press was relatively new. It was only a few hundred years old at the time. So libraries weren't a big deal. And so this dude who was an Austrian monk, pretty much all he got to do in life was go do the prayer stuff, because they did a lot of that. Copy a few manuscripts. Wait for the monastery's brandy to properly prepare itself. So to entertain himself during his waking hours, he decided to grow peas. Now, if you're familiar with peas, even if you're not familiar with peas, I'll tell you now that actually pea vines, the flower on them is quite pretty. So this is this poor guy stuck there, no internet, nothing but Bible and booze. Sounds kind of like that. Doesn't sound like. So he grows these pea plants, and for some reason, he must have hit his head on a low ceiling at some point. He decided he was really interested in what the proportion of purple pea flowers was to white pea flowers, because it never made much sense to him. So he decided, after a little bit of observation, that he thought that 75% of pea plants would produce purple flowers and 25% would produce white flowers. So he decided to test his theory. And so perhaps you've heard of this guy named Mendel. Apparently he's the father of modern genetics, which is funny because if he was a monk, he wasn't a father of anything. But we're going to use that, which you will. Do they make you all take biology anymore, or is that kind of an option?
I already did.
Okay, so you learned about pea plants and Mendel's there. Did they ever tell you about how amazing it was that all of his records, he never had anything he couldn't classify? It's like he was cheating on behalf of dog, spelled backwards. But we'll put that aside. So he came up with this conjecture. We're going to go ahead and use that as a motivating idea for some hypothesis tests. That's the whole point of it. If you're interested in it, you can read more about Mendel in his autobiography called I Got It From My Mama. Yeah, I also don't think he really wrote it, but yeah, this is, once you get to graduate school, you can actually read real materials. So yeah, not this this crap. Yeah. So let's suppose we want to assess Mendel's model of the world. We can use all the tools that we've already learned and do it. We can simulate growing pea plants, and in a computer we could simulate thousands and thousands of seasons. Unlike real life, to simulate thousands and thousands of seasons, we'd have to live an awful long time. That would take some serious prayer and serious Gregorian brandy to even have a hope to get there. And our goal will be, let's see if Mendel's model was appropriate or not. Let's see if he's right. If 3 parts out of 4, we're going to get purple flowers. So what we're going to do is we will generate a statistic, and a statistic is just a fancy word for some kind of calculation to produce a measurement. And the statistic we're going to choose is we're going to measure the distance between our observed mean value of our sample and 75%. And so if indeed we take a sample of a growing season, which we'll do in the computer, and we get 75% of the flowers are purple, compared to Mendel's model, which is 75%, the distance between those two is going to be really small. It's going to be identically close to 0, the smallest number in the alphabet. Whereas on the other hand, if our estimate is not that good, we would conclude either our estimate's bad or more likely Mendel's model is garbage. So our statistic in this case will be called the distance. And if nothing else this afternoon interests you, this might be the best part. So the word statistic was invented by statisticians and mathematicians to scare the rest of us. All a statistic is some kind of measurement. So what are some of the measurements that you're familiar with, at least from this class? So one of the measurements we had was central tendency. What was that called?
I know it as like the bell curve, but it's not.
No, the measurement of central tendency is mean.
It's the mean.
What's the measurement of how spread it is? Because you're the spread guy anyway. You like playing the spread. What's that measurement called?
That's standard deviation.
Okay, all those are calculations. They're just measurements. So a mean, an average is a measurement. And so we call that measurement, another name for the measurement is called a statistic. So there, I've just wrecked statistics for you all, but that's okay. You have to find something else to be scared of. So in our case, the statistic for this particular example is the distance of a value that we compute based on a set of observations and 75. So we can pretend that Mendel's model is true, and we'll use a sample proportion function to simulate the distance under the assumptions of the model. First, we got to figure out how many times to sample. To do this, remember, we're going to compare our simulation to Mendel's actual experiments. So we should simulate the same number of plants that he grew. And this particular thing, I'm taking it from UC Berkeley. They claim Mendel grew a lot of plants. In fact, 929. Now I looked at the picture of that garden. You saw the picture too. I can't figure out how those how 929 divides into those 6 plots at all is an integer thing.
He did have 30, 40 years.
Indeed, he did.
And
And
nothing else.
but getting drunk, reading the Bible, and growing plants. Not a bad job if you can
Probably
get it.
all 3 at once. Not much.
So we'll do 929 samples to kind of replicate his experiment. So here's the steps. We're going to sample 929s at random from a distribution specified by a model and find the sample proportion in the purple flowering category, multiply that by 100 so it's represented as a percent, and subtract from that value 75, take the absolute value of the difference between the two, and that will be our computation. That will be our statistic. That'll be our measurement. So first we start by defining a function. And now we're actually getting silly with our function naming. This is probably the best named function in the history of functions. So the name of the function is distance from 75. The excellent function, unless you're trying to find the distance from 50, in which case you need a different name. And it's just returning the absolute value of 100 times whatever proportion we provided minus 75. Now to simulate a single value of the distance between the sample percent of purple plants and 75 under the assumption of Mendel's model, we'll first simulate the proportion of purple plants from 929 under the assumption that the model is indeed producing 75%. And so we're now defining a critter called model underscore proportions. What type of data structure is model underscore proportions? A list. Excellent. The contents of that list are what type of data? Floats. Good. You're done. Class is over for you. You can leave. Model proportions is a list that has 2 things in it. The left thing is the fraction of purple flowers. The right's fraction of white flowers. And we have another object called proportion underscore purple underscore in underscore sample. Those people at Berkeley really like to type a lot. And they're using a module called the data science module. We don't need the data science module, but it reduces the amount of scripting by a fair amount. So we're just flat out copying it. And it's going to sample proportions from, I think it samples from either a normal or a binomial distribution. I'd have to read, but that's just too much for me. It's going to do a 929, and it's going to attempt to produce sample proportions that have one fraction is 75%, one fraction is 25%. So we've done something similar to that already. When you did the NumPy dot normal dot sample, and you told it how many things, mean and standard deviation. Remember doing that? For those of you that were here when we did that, those of you that were watching cat videos, that was when we were looking at the tuxedo cat chasing the fake mouse. So we've done this proportion of purple, and now we feed that to our distance from 75 function. And in this case, in this particular example, whenever I ran it, it came back as 1.85. So it said, we think it's 75%. We got a value that was 1.85 away from 75. So 76.85 or 73.15, something in that range. That's still pretty close to 75 in the whole scheme of things. That we'd probably keep it, but we'll just pretend that we're too stupid to make that decision. So that's one simulated distance. Now, because we want to do this a lot, Mendel only had one lifetime, so he could only do 929 plants. We have a computer. We're going to go ahead and do it 10,000 times. So that's 10,000 lifetimes. Or that's 10,000 monasteries all doing it one time. That's still a lot of Gregorian brandy right there. Somebody is going to have trouble driving the hay cart. So we'll do 10,000 samples. Basically, we'll replicate the actual experiment 10,000 times. And as before, first we use the code we developed to make a function that does one value. So there's one simulated distance. They're going by the rather cleverly chosen function name, one simulated distance. And then we're going to go ahead and make an array called distances. We'll repeat it 10,000 times. And as it's marching through these repetitions, we will add the simulated distance for each growing season. So we've just simulated. So if you figure Mendel lived to, how old did monks in the 1800s live? Let's say live 50 years. So we've just done 50,000, half of that. We've just done 25,000 years of monks, each growing plants. That would be a very pitiful existence after about the third lifetime. But anyway, so it's going to just keep regrowing and regrowing. And finally, we can get the length of distances. We should find out that it's should be 9,999. Actually, no, the length should be 10,000. The indexes will be 0 to 9,999. So we've done that. And now when in doubt, we always make histograms or we draw pictures. Why do we draw pictures? Because we can choose cool colors and hopefully deceive the client, that'd be me, from knowing what's going on. So there's a histogram of our 10,000 lifetimes of growing pea plants. And remember, our null hypothesis was that the mean value of purple would be 75%. And as we move away from that, the distance goes up. So there's our histogram. How many of those lifetimes did we indeed get a proportion that was pretty close to the mean value, to the 75%? So we got a distance of between 0 and 0.5. We roughly saw about 3,250 of those. 3,250 lifetimes, we got a value between 0 and 0.5. Another 2,500 lifetimes, we got a value between 0.5 and 1. So we put those two together. So a distance of 1 means that it was 74% to 76%. So we put those two together. So 3,000 and 2,500 is 5,500 lifetimes. More than half of the lifetimes, we saw something that was within 1 of 75%. Very few lifetimes were spent finding things that were distances of 6 away. So what's the chance of any sample having a value, let's see, do this in my head, of 69% or less, or 81% or bigger? Means we're out here. Yeah, pretty unlikely. You'd have to go get another 100,000 monks to be able to get some of them out there. And of course, the computer is so tired from computing that it's got to take a break. There we go. Looking at that picture, where does it look like the balance point of that distribution is? So now you have to do some engineering thinking. If each of those represented a uniform weight, how would you get this thing to balance? If I put my finger here and set it on my finger, which way would it fall? Fall towards me. If I put my finger somewhere around here, it would balance. That's the balance point. Balance point is what we call a median, or the mean. Probably in this case, the median and mean are really close to one another. So let's find the values for distance for the 25th percentile, 50th, 75th, and 99th percentile. So I just balanced this on my finger and decided that the balance point, which would represent the 50th percentile, should be pretty close to 1. I think it'd be a bit less than 1. And sure enough, 50% of the distances are between 0 and 0.94. 25% of the distances are between 0 and 0.46, 75 between 0 and 1.64, 99% between 0 and 3.69. So the chances of seeing a distance in any single sample of, say, 5 is pretty small, really small, in fact. The median distance slightly less than 1, and so forth. So we can change the label on the histogram to make it look cooler, because that's very important to make stuff look cool. And we can actually compare the prediction in the data. So, for example, in one of the experiments that Mendel grew, he got 705 purple flowers, which works out to 75.89%. And because Mendel was dealing with discrete things, he had to have integer values. That's why he came up with 75. So the observed value of our statistics, the distance between Mendel's sample percent and 75, is about 0.89 in that particular example. Just by eye, if we locate where 89 is, it will be on that blue dot right up there. So we've redrawn the histogram, and now we've actually done a little bit of decoration by putting a dot up there, which is not blue, it's magenta, but that's okay. If we use the data science external module, they can do almost the same picture, except they only get half dot because of where they selected to put the y-axis. But they're UC Berkeley, they must know what they're doing. So we actually can put markers on a histogram if we want. We could put a 25th percentile marker. We've got the 50th percentile and so forth. Okay, we can further find quantiles associated with a particular observed statistic. So if we got a measurement of 0.888, we'd find out that that is smaller than 54.85% of the, please let me scroll the output, of the simulated, I think it's sample. So what we've actually done is presented kind of a twisted story on a hypothesis test. We've tested the hypothesis that the value of any measurement on pea flowers should be 75% purple. In this case, we use simulation to replicate many experiments. And what the statistical geniuses have done, they've done that already for a lot of things. So there's certain statistics that they present to us and said, if you make a measurement in this particular fashion, that measurement should follow a normal distribution. If you make a measurement in this particular fashion, it should be a chi-square distribution. And that's what introduces a statistical test. Recall from last time, the four essential elements are the null hypothesis, an alternative, some test statistic, and the reject region. Everyone loves the reject region because we spend a lot of time there. Suppose we wanted to test a hypothesis concerning some parameter theta based on a random sample y1 through yn. So the random sample is the thing we collect. The parameter is the measurement that we make. So what's our most famous, our most favorite parameter that we make in almost all statistics books, certainly in this class? It's the angry value of the sample. No, a mean value. Mean, so the theta up there could be the mean. It doesn't have to be, but just put that in your head if you're having trouble dealing with these letters in the Greek alphabet. And so we estimate the population parameter theta based on its equivalent sample parameter, theta hat. So all the sample parameters wear hats. And we'll assume in this case that the estimator is approximately normal with a mean of theta and a variance of sigma squared. So now suppose that we have a particular target value of theta, in this case theta sub 0, and we want to test the conjecture. I postulate that the population parameter is equal to theta sub 0. That's my postulation. That's my Mendel's decision is 75% purple. And I further postulate that if that's not the case, my alternative hypothesis is that the population parameter is bigger than theta 0. So how many tails is that test going to have? One. Yeah. The picture below is intentionally confusing. It's showing various distributions of theta hat. Remember, theta hat is an estimator that we get from a sample for different values of theta sub I, including one that happens to center on theta sub 0. So if in some particular sample, we're sampling whatever the population, some sample, let's say we get a sample that happens to fall right there, and we think the population one is here, we're probably going to conclude that we're going to reject our null hypothesis in that case. But as we start to get closer and closer, depending on the sample, so these things are coming up every time we make a sample. Every time we did those 10,000 lifetimes, each one produced a different one, but most of them kind of hovered around here. And that's why we selected to not reject. So if theta hat happens to be close to theta 0, it's reasonable to accept the null hypothesis. However, if that's not the case, it's more likely that theta hat's going to be large. Thus, large values of theta hat relative to theta sub 0 favor rejection of the null hypothesis. No surprise there. And the acceptance of the alternative hypothesis. And there I am violating my rules from last time, but I stole this from other people because, like you, I'm too lazy to write this stuff entirely by myself. Using those four elements of a hypothesis test as a guide, we can make this cool looking table right here. Left column item, right column is the value. So our null hypothesis is theta equals theta sub 0. Our alternative is theta is bigger than that. Our test statistic is theta hat. That's the measurement that we make of our sample. If in this case theta happens to be the mean value, how do you compute that measurement? You just compute the mean of the sample. And our rejection region is we will reject if theta hat, our measurement, is bigger than some value k, and then we last time discussed at some length how to get that value k. Generally, K is something that we pull out of our datum by trying to set the type 1 error probability spelled incorrectly. Alpha, that probability alpha, and that will help us choose what K is. And again, because I copied this from somewhere else, according to the figure below, and apparently whoever wrote this from where I copied it, that was enlightening in their mind. So we choose an acceptable error rate. We call that, what letter of the alphabet? Greek letter, looks like a fish, alpha. Once we choose that error rate, assuming that we know, we have assumed an underlying distribution of our sample, we can figure out what value our sample statistic, our sample measurement has to have, so that if it's bigger than that value, we're out here in the error region. So that's all that selecting alpha does. We select a value from alpha, of alpha. We have this distribution that's based on our sample. We go ahead and we integrate that distribution until what's left is the alpha region, and that identifies the breakoff point, which we call K. So let's suppose the distribution is indeed a standard normal distribution. So mean of 0, variance of 1. Excuse me, well, yeah, variance standard deviation of 1. Let's suppose we choose a rejection region of, let's see if I do this in my head, 5% on one side. So the center has what value? Standard normal to 0. We go 1 standard deviation. We can account for plus or minus 166%, and we have the other amount there. And so eventually K is going to be, I think 2.6 standard deviations will be the cutoff value. And then we can rescale that into the scale of whatever our actual observations are. So that's how K comes about. For example, K could be theta 0 plus the z-score associated with alpha multiplied by the variance, and it's right up there. So that's where we get K from. So K is not some magic number unless they don't tell you how to find it. And so our rejection region can be restated as, we will reject when our measurement statistic, theta hat, minus theta 0, the value we're testing against, divided by the sample standard deviation is bigger than the z-score associated with 5%. Where do we get the z of 5%? In your statistics class, you'll look it up in a table in the back of the book. In our case, we can just go ahead and generate a normal distribution and integrate it until we get up to 5%. So that's something that we have to do, calculate or look it up. And now our test can be stated in the actual useful manner as H0 is theta 0, H alternative is bigger than, test statistic, that's how to make the calculation. And we reject when Z is bigger than Z sub alpha for an arbitrary choice of alpha that we, the analysts, get to choose. If there's not too much severe loss of life consequence, we could probably make A fairly biggish. If it's my money, I would make A fairly small, which means I would reject in almost any circumstances. If it's your lives, I would go ahead and make A 50%. So almost guaranteed that you wouldn't walk off campus today. I'm just teasing you. So let's look at an example. When we get done with this example, I'm going to hand you off so you can spend the rest of your Friday afternoon, where it's nice and warm out, with your best friend, Josh. We tease him a lot when he's not here to defend himself. But okay, so imagine we're in a factory and we have a stipulation by the factory bosses that a machine has to be stopped and maintained when its defect rate exceeds 10% in daily production rates. Okay, so this machine makes things. What do you want to make? Most people like to make widgets because it's just a funny thing, or gadgets.
Sure.
I want to make hot dogs. So we are at the Der Wiener Schnitzel supply factory, squirting out hot dogs on a daily basis. And when the defects exceed 10%, we need to shut the machine down, pour a couple of gallons of Clorox bleach in it, sweep the dust off, and restart it, and put more hot dog mixing in. Okay, so you will never forget that example. You also never eat a hot dog again. So as we're doing that, we let the machine run and we randomly sample 100 items from one day of production. And we find out that when we supply that sample to 15 of our best employees, they drop over dead. And so the shop foreman claims, well, we have to go ahead and do the maintenance and repair on the machine because 15 exceeds 10%. So let's ask ourselves, does that particular sample contain enough evidence to support that the machine is defective and needs to be maintained? I mean, at first glance, yeah, it looks like it does. Random sample of 100, 15 items are bad. That's bigger than 10%. That must not be right. But since maintenance takes the machine out of service for a while, what happens when our hot dog machine can't make hot dogs? We don't lose it. We just don't make money. We can't make money.
I mean, does the
Opportunity
usually
cost.
go bad?
I'm saying opportunity cost. Every minute we're not making money, we're losing money.
Right, and because we have to maintain the machine, so we can't have the machine maintenance staff sitting there at their internet website trying to scam people out of their passwords. Because that's how we make real money. You know, making hot dogs, it just sort of keeps the lights
You
on.
round up the coins from their Bitcoin.
Okay, so yeah, we already studied that. Yeah, when you guys are done with this class, what have we done in this class? We've taught you how to gamble, play Russian roulette,
And steal from
and steal from people.
Hey, but children in buckets.
Yeah. So
Whoa.
you slept through that one, dude.
What
Okay.
are you gonna tell us about the project?
Oh, shit. Will you email me and tell me to do that on Monday, pretty please? Thank you. Everyone else thanks you too. Cool. That means I don't have to come up with a full lecture on Monday. We'll talk about projects. I apologize. I did say we do it this week. I'm sorry. I can tell you in general terms about the projects right now. There's 2 or 3 of them linked. And what you do is we want you to do it in teams. So find your 3 best friends or worst enemies. The invisible people are screwed because I don't know how they're going to find a team. A team of 3 or 5. 3 is preferable. Don't do a team of 4. Because on the off chance that you end up with 1 or 2 assholes, you'll never be able to agree. If you have an odd number, at least you can override the asshole. Oh, then you have pretty much the current global situation on this planet. So. And they're going to make you do team projects throughout your time here at Texas Tech. These ones early in your career, for those of you that are authentic freshmen or just like sophomores having to take this class because it creeped up on you and you couldn't escape it. You want to use these experiences to identify useless people, because in your later times, you'll actually get to choose who your team is explicitly. And usually they let you say, who are you absolutely unwilling to work with? And that's when you pull your list out and you say, worthless person 3, 7, and 10. I will not work with them. So you want to go see the projects, Elizabeth? Sure you do. Yeah, I'll let Josh do the foreman one because he did that this morning. So he's very good at it. Projects. Project collection. So there are, looks like there's 3. These are the 3 we're going to stick with. If you go and click on them right now, the dates are going to be wrong. One of them is concrete strength prediction. You've actually seen the database already earlier. And we go look at what one of the projects looks like. A little background, the objective would be a literature scan on concrete design, utility of predictive approach. Why would you want to be able to predict concrete strength? Analyze an existing database, build a data model to predict the compressive strength of a concrete mixture, build an interface to allow you to enter mixture information, and then build an interface to allow users to add observations to underlying distributions. A little bit of references to get you started. Database acquisition, and then here is a test case, and there's no answer given here. So using your best model, determine the projected concrete strength of these 5 mixtures. And then documentation, and what you're supposed to produce is effort sheets due each Friday, an interim report, which will not be due November 24th because that's the wrong semester. It'll be due, we'll get those fixed by Monday. And then a final report. And in the past, instead of having you come up here and present to the class, because transitioning people, it takes too much time, your team can get together on Zoom and make a video. And the video has 2 parts. First, you demonstrate your final result and description of any problems you couldn't solve. And the second part of the video is do a project management. That's where you identify how you divided up the work, who did what, and who the person on the team that never showed up is, but the name had to be on the report because we couldn't figure out how to terminate it with extreme prejudice. So that's one of the possible projects. We'll take a quick look at the other 2. Next one is stream analysis. That one's cool because it has a moving picture, but it's very much a similar kind of problem. A little bit of background, cool pictures of dams and gauges, how stream flows measured, Colorado River in Texas, the data set, meteorological data set. Then you go ahead and you get the stuff, and then the problem statement, literature scan, build an interface, analyzing existing model, build an interface to allow relative input, document, and the model building part. This particular one, I think this particular project is best done using a technique called logistic regression. Same deliverable list and same due dates. Obviously, these ones are not appropriate for this semester. And then the one that is usually quite popular, especially for mechanical engineers, because you have to do this in a lab anyway, is an instrument calibration problem. So you have this instrument and you have to learn about instrument calibration, analyze an existing database, and basically come up with a calibration curve for a transducer. So those are the projects. Thank you for asking. Is that a good introduction? I'll wait till she's done scratching her ear. Is that a good enough introduction? You got a rough idea? So between now and next week would be a good time to identify what team you want to be.
What did you say it was due?
When's the project due? It is, I think it's due the last day of the semester.
Oh,
It's due whenever the final exam would be in this class. We don't have a final because the instructor team, myself included, realizes that's kind of dumb. So at the 3rd exam is administered the last day you're allowed to give an exam or that. And after that, the only gradable thing you have left is the project. Because I know damn well nobody is going to turn in lab 32. I'm going to do that since I've done 31 of these things. Screw that. I'm not going to waste my time. So all you have left is the project. I think actually I talked to Dr. Danimo. I think we have a couple of days scheduled in the next, not next week, but after the next exam, we'll have some workshop days. So as your teams are working on projects, instead of doing lecture, we can talk about individual projects. I don't know if that's actually shown in the syllabus or not, but there is intent for that to happen. So the 25 of you that are physically sitting in this room, you all should team up with someone else who actually comes here alive and avoid the invisible people. Because invisible people have a bad tendency of not being a good contributor to a team project. Oh, I said that on recording too. Well, that's how it is with invisible
Well, that's on
people.
record.
Let's be honest. Are they really gonna hear that though?
Well,
Yeah, right, then
Well,
being
then they'll
invisible,
make
it's
them
not
go to
just,
class.
yeah.
okay, since you asked the question, let me stop the recording. So Carson asked actually a very interesting question.